Thank you. Where's the clicker
It's on
thing?
the further away
right.
table, sorry.
All right. Thank you so much to Gaia for having me and for organizing this fantastic get-together. I'm really excited to be here to talk to you about this retrieval augmented generation for threat intelligence. And let's see how this thing works. So I think I was here at Gaia 5 years ago talking about large language models, and that was exactly when BERT had come out, I think. So I talked about BERT and GPT, and 5 years has passed tremendously fast. And even though it feels like a long time ago, the pace at which the sort of AI and ML community has moved is incredible to me. So I think my talk back then was called A Language Model is All You Need. And I think we're here today to challenge that assumption, a little bit at least. And I think, like, in terms of working as an NLP scientist in this space, one of the most fundamental shifts has been exactly this, that now we only talk about machine learning models in this context, at least if you're in the NLP space. So it's text in and you get text out, and you have something in between. So before this, it was much more, you talked about vectors, you got numbers out that you had to interpret, but now it's like natural language to natural language. And I think just that interface is so interesting and has so many potentials for future applications. But I guess almost everyone here has some experience with language models. You basically ask something, you get a reply back. And this talk will be mostly focused on intelligence. So of course, we ask questions to language models with the intent to get some information. So here I asked a question to the one and only GPT. And I think this sort of tells you when I made these slides, exactly after the Academy Awards. So I asked about who won the Oscar for Best Picture in 2016, and it gave this spot-on answer. I haven't seen the movie. It looked great from the IMDb sort of page. But what about if you actually wanted to do something for what you care about, your domain or your business or what have you? And in our case, we are dealing with threat intelligence. So I asked it the following question. So what can you tell me about Akira ransomware group? And then we get this answer. So as of my last update in January 2022, I think you've seen these types of answers before, but it can't give you any real information. And really what we want to do is to understand how you can bridge that gap, basically. How can you sort of connect these LLMs to what you care about? So there are a few ways to go about this. So the first one is just to hope that whatever language model you use has this information. It could be GPT, Claude, Mistral, whatever you want to try. But as we saw in the previous example, it has limited success. So the other sort of mode that you could embark on is to sort of regress to fine-tuning these types of models. So say that you have data, you try to fine-tune with the aim of getting this knowledge into that model that you're using. But of course, this is extremely cost and time consuming, and it's very hard to keep track of, like if you add knowledge, do you push out knowledge on the other end? How does that work? It's a very hard mechanism to control. And then you have what we will talk about today, where you basically build domain-specific prompts in a specific fashion. So I tried this with GPT as well. So I just pasted some information that I found partly on the web, but also in our system, the Record Future system. So now I have the prompt which reads something like this. So below is some information about the Akira ransomware group. And first I put some entity information about what that group is, like aliases and other things. And then I pasted some fragments I found from the internet in terms of what they have been up to. And then I asked this question again. And now, even though I have to cut the answer here, you get an actual informed answer from the LLM. So basically, this is a great way to build the bridge between LLMs and harness the power of LLMs for your own domain, to build an interface layer between your data and the LLM. And that's what we will talk about today. And this is usually referred to as retrieval augmented generation. And schematically, it looks something like this. You have some user input in terms of text. And now you inject some sort of data interface here that interfaces to your data. And it retrieves, hence the retrieval part of retrieval augmented generation, retrieves data from your system and somehow puts that into your prompt. So basically, we're trying to automate this whole process. And then you get some output text. You feed this prompt into your LLM, and you get some nice result back, hopefully. So I think when this was popularized maybe a year or so ago, the main mode of retrieval was using embeddings. And I'm sure most of you here today knows a lot about what this means. But basically, you have your domain data, you have some embedding model, and you feed all your data through that embedding model and put that into some vector space. I have painted it here as two-dimensional, but I think you know it's much higher in reality. And bear in mind that this, even though, I don't know, it's 15 red dots or so here, this is usually a non-trivial operation because, like at Recorded Future at least, we have terabytes and terabytes of red points that we could put here. So that is, that can be costly. But in any case, you get your data into this vector space, you take your question, and you embed that as well using some mechanism. And you get another vector from that. And then you have some notion of closeness that you can define in various ways. And then you say something like, OK, I will pick the top k points that are closest to my question. And these are the data points that then go into the prompt. So this was the very traditional way of how things got started. And I think this is because this was a very simple way for everyone to sort of get quite good results with minimum effort. But I think, as we will see today, this has a limited appeal in many cases. So more schematically, what we will talk about today is where you have the data interface, you have the LLM, but you also inject this layer of domain logic that I think will be needed in every sort of RAG application that you would try. And this is very tailored to whatever domain you're in. And this box down there is what we will talk about today. So just to make it crystal clear, like what we're aiming for here, is that I have the same question up here. We will build something like this in terms of this prompt automatically using various heuristics that make sense for our domain. So when doing this using our system, the Recorded Future, this is what we got. So I asked the same question to Recorded Future AI, and I got a very nice answer here in terms of what the Akira ransomware group has been up to. So with that, let's move a bit into threat intelligence. So this, a lot of text here, but basically I really like the wording. So threat intelligence is about data collected from diverse sources that has been organized, analyzed, and delivered to understand the threat landscape, threat actors, their tactics, behaviors, and targets. So this really puts data and the organization of data as the centerpiece of threat intelligence. And we have organized that into what we refer to as our intelligence graph. And basically, we have lots and lots of various data sources. These comes a lot from open source web that we run through some information extraction pipeline, and then these will end up in our intelligence graph. And here in this cogwheel square there, we have things like NLP and image entity extraction. So it's really a multimodal type of thing. We also have a lot of structured data that we put in here, as well as I said, images. And this is something that keeps on running 24/7. And I think we actually add somewhere close to 150 million nodes and relations to our graph every day. So as you can imagine, this is a quite big apparatus. And just to give you a clearer flavor of the type of data that, or some type of data that we're working with, I have this example here where we have what we refer to as references. So these could be things that we collect from websites, mainstream news, etc. And then we have some way of first classifying that into various things that give a signal. So in this case, we have a reference that we have classified as a cyber attack over there. And from this, we have also extracted sort of, well, who was the target, the French government, who was the attacker, anonymous Sudan, and what was the method here, and that was a DDoS attack. And all of these things go into our graph then. So basically, we have a graph of a bunch of events, and these events are references that contain text. And these are the text blobs that we want to put into our LLM eventually. And a bunch, lots and lots of entities that forms a sort of an ontological structure that we can sort of navigate through. And one very interesting aspect of this is that it also is multilingual. So this is in over 15 languages that we do this. So whatever we build need to be sort of support the multilingual use case. Okay, so with this we have built, so going sort of a step further than just the vector space retrieval, we have built a thing which sort of extracts the salient points here. So here we're talking about cyber attacks, companies in Sweden in the last month. From this question, can you give me information about cyber attacks against companies in Sweden in the last month? And from this we have sort of a way of querying this graph. And this is very schematically here, but we have some box here that converts this into some query language from which we can extract data from the graph. So with this query language in mind, we sort of have a nice symbiosis between the intelligence graph and sort of our vector database from which we can extract things to put into the prompt. And basically the way it works is that we take the user input, the text, converts that to a query. From this query, we get all the results from our vector database. So that's the 1 here. And with 2, we take all those results that we got back from that query and embed that into vector space. And in 3, we sort of use some complex, fairly complex logic, which you can see as the sort of closest retrieval logic before in the vector space to actually get the references and text that we want to put in the prompt. And I think this is, like in terms of building this feature first with speed so that it works fast. And this was really one of the things that we had to spend a lot of time on. Because you could think like the other way around here would be to start with embedding all your data in your graph. But that is, as I alluded to in the beginning, a very big operation. So this sort of makes us incrementally able to build up this vector space while still keeping the sort of integrity of the data by querying the graph at all times. And this 2 part here with the embeddings is also where we had to spend a lot of time to speed that up in order to make this sort of real-time usable. So just to summarize here, so for 1 here, we get the references by this query, we embed the references, and then we have some similarity search ++. in which we sort of get the actual references that we want to put in the prompt, or the data that we want to put in the prompt. So, and while this looks quite simple and two-dimensional, in fact, we have many, or at least a few of these vector databases that we query here in this logic. So it's not as simple as it looks here. And that means that in this thing here, information that goes into the prompt, we can have many references to actually put in. So that means that we have had to spend quite some time in sort of increasing the signal in the information that we put into the prompt. So here we might have hundreds, and even thousands of references, and we want to sort of bring that down to a better number, because even things like the mighty GPT or Mistral is not sort of immune to the crap in, crap out paradigm. So the more signal you have, the better it will work. So in terms of improving these systems, this is where a lot of that happens. Another thing that we have spent quite some time doing is to use our graph to define user, for the user's meaningful context that we can use in this retrieval system. So basically, this means that we have a bunch of defined concepts for our users, and the users can also set these themselves. And what these really are is sort of nodes in our intelligence graph. And with these concepts, we can sort of restrict the space from which we are retrieving to certain contexts within this graph. So for an example there, a user's technological entities, like what their tech stack basically is. So it works something like this. So the user might ask, how are my technologies exploited? And we then sort of translate this into a context into the graph and use that to really filter down what type of references we bring back. And that helps a lot in sort of increasing the user experience of how, like what type of information you really want to get. So in this case, of course, you can't really see what these nodes that we restrict to here are, but the answer we get is really tailored to sort of that portion of the graph now. So this is one of the examples of like a very domain-specific thing that we have had to implement it to make this make sense. Another interesting example are questions like these. So a lot of the questions that we are trying to solve are of this nature, where it's not really, you're not really looking for one reference that might give you the answer. It's rather the collective set of knowledge that you can find on the internet that you want to reason about. So this is one of those questions. So which were the 3 biggest cyber attacks in Sweden last month? So of course you won't find like a page describing exactly what they were. So it's more about inferring that from all the data that we have. But of course, if we do our standard retrieval here, where we have the cyber attacks, we have Sweden last month, we get a bunch of references that we would like to put in the prompt. We could get thousands and thousands of these. And the LLMs are not great. They will give you an answer, but they are not great at giving the correct answer in these cases. So you have problems with that there are many data points in here, and how do you determine which were biggest, or even what biggest means in this context. So for this, we have had to build like alternate versions of the data interface, where we take the user input, we understand that it's more of an aggregate type question, and then we basically use map the questions to an API, which we can query the graph for sort of aggregate versions of these questions. So you see here, for instance, I somewhat heuristically put here, this user input that we saw before would be translated to something like this, like compute aggregates, type aggregates top, and you have the query here, and you want the biggest 3, or something like that. So, and this is very important in able to actually truthfully be able to answer that type of questions. So to sort of summarize the system that we have is that we have the user input. Something I didn't talk too much about here is that there are a lot of different use cases that we actually support, and they require quite a different logic. So we have a use case router first, which sort of understands what logic is it that we want to employ for this question. We have all these data interfaces, and as I mentioned a bit before, we have slight flavors of these depending on the use case router, what that says. And then we have this retrieval logic here, which sort of gives us the nice output. So, and to sum up sort of the domain-specific things that we have been trying or having to tackle in order to get this into a good shape. I mean, first of all, it's the organization of your data. So that is still key. I don't think we will ever get away from data being the key. This natural language to sort of query language has been a key part as well. Ontology information, I didn't go into this too much, but given the question, we have heuristics to sort of go through our graph and find what type of information do we have in our ontology that we should feed into the prompt. You saw some examples of this in the beginning, but that is something where we have had to spend a lot of time. Aggregation and statistics to be able to ask more trend-oriented or aggregate-oriented questions, which are prolific in this setting. Ranking and filtering, and I can say like a lot of the, it depends a lot on the use cases how you deal with this. And for our uses, we've had to tinker a lot with like what type of entities and what type of concepts are the user actually asking about, and sort of trying to map that to a score that gives a better ranking, basically. We have the use case classification, basically routing this to various parts of the system, as well as the context modeling. And in all types of intelligence, one of the most important things is how do we understand if the answers are correct or not. So we dealt with this in the following way. So here we have an example from the recorded future AI, where please list 3 ransomware attacks in Sweden in the last month, where it gave three answers here. And you see we have these quotation marks or quotations numbers up here. And so if we actually look at how this looks in our product, it looks something like this. And if you click the 3 here, you get all these references here that actually went into generating this answer. So here the user can actually understand and read and make sure that this is a true statement based on facts. And this is extremely important in terms of analysts actually using this data. And there are many ways of going about how you would actually implement this type of solution. But what we ended up doing, and we had many experiments with this, but this turned out to be the best performer, is basically that, okay, we have all the data that went into the prompt, these references that we saw before. So we embed those into vector space. We get the response from the large language model. So in this case, I took the 3rd sort of bullet point there. And we also embed that into this blue little thing here. And then we can do one of 2 things. Either we can take the data points that are close by in terms of some metric, cosine distance or something like that. But we can also use the entities that we have found here and make sure that we can also pick out points here if they sort of contain the same entity in terms of the knowledge graph. So basically all of this goes into providing the actual proof here of making sure that it's correct. And more importantly, for the analysts who is ultimately responsible here to actually be able to check that it's correct. Okay, so basically, I think the takeaway is here that large language models are awesome things, but to get them to work for you and for your use cases, like when they were introduced, I think a lot of people got their hopes up in some sense. But then they figured out that we need something to actually be able to harness this power for like what we want to do. And what I have talked about today is a great way of doing that, I think. So you build some sort of domain-specific data interface that you have sort of between your LLM and your data. And I think this will become, like in terms of what we will see in the future, this will become the sort of reigning paradigm. And I think that the data modeling part will become even more important, that you actually model your data in a semantically sort of valid way, so that the sort of distance you have to cover between the LLM and your data is smaller. And I think we will see LLMs that are actually tailored more towards actually fetching data from data sources. And I think we will see a great love story between these in the future. And I aim to be part of that future. And with that, thank you so much.
Thank you so much, Aron. Allow me to ask you the first question very rapidly. Of all these external components, external to the basic RAG solution that you were describing, which one is the one that is providing the most success in terms of accuracy, contributing the most thinking? Is it the ontology, the organization of your data from the very start, or the ability to define a context?
I think that's as with all these problems, it's very hard to, it's like you have to fine-tune all of these components in tandem to get the most out of it. So it's very hard to just say that this is the thing you need. Of course, like without the data interface, you have nothing. So I would still argue that that is the biggest component here. But it sort of goes hand in hand with everything. And it really is like if you tweak something here, something there will break.
Yes, thank you. Please, questions from the audience. Yeah, we have Judith and Fatima on the. We have a question on this side, Fatima. But also Judith is going to our first question here. Judith is. Yes, please, once you raise your hand, keep it raised, because we have also many hands on this side.
Thanks for a great talk. I was curious if you were using LLMs for more tasks, like the natural language to query translation.
Yeah, that's a great question. I mean, it looked like one LLM, but there were some arrows going around there, and that's exactly why, because we use, I think for each question here, we use somewhere between 5 and 10 LLM calls to actually do things like natural language classification, etc. So there are lots of LLMs involved in every answer here, more than just the final prompt.
Thanks.
Yeah, thanks for the question.
Next question, please. Yes.
Yeah, hey, thanks for the talk. We're wondering, why do you have to go in the data interface via the embedding space? Why don't you have that information, what's closely related already in the graph?
Yeah, so this is basically a bit what I was answering Daniela as well, like the balance here. So of course, if you get everything 100% right in your query to the intelligence graph, that is really all you need. But to be sort of on the safe side, it's better to actually, or we have seen in our experiments that it's better to get also things that we get via something like vector similarity, and sort of combine those two modes into one single prompt, and then sort of use that and filter down from those set of references.
Thanks.
Thank you very much. Aron, do you think you can make yourself available for questions afterwards?
Absolutely.
Because actually we need to move on, but I would encourage you to approach Aron afterwards.
Please do. Thank you.
Thank you so much, Aron.
Thank you.
And
I have nothing
yes,
here.
and please accept these
Thank you.
flowers from
Thank you.
us.